Hello everyone, welcome. We are going to look at edges, corners and blobs, starting with the edges. So we have been looking at intensity transformations and then spatial operations, or spatial filtering. This we affect by having a transform from input pixel values to output pixel values and using CVLUT to affect this transformation. So by choosing the transformation, we can affect different kinds of intensity changes that actually affect the brightness of the image. So when we think about these intensity transformations, the corresponding output pixel depends only on the input pixel. But when we consider spatial operations, the corresponding output pixel depends not only on the input pixel, but perhaps a neighborhood of the input pixel, say a 3 by 3 neighborhood. So we do this by selecting the right kernel, this 3 by 3 kernel for example, and we call it sometimes a filter, sometimes a window, and using CV's filter 2D to carry out the convolution operation. Since our filters are symmetric, this is equivalent to correlation. So with a spatial filtering, we are able to do smoothings like Gaussian smoothing, or average filtering, or we can compute gradients using, for example, Sobel kernels and so on. So you can see in intensity transformations, we choose the input-output transformation. In spatial filtering, we choose the correct kernel so that we can get the effect that we desire. So by building on this spatial filtering, we will look at edges, corners and blobs. Okay, I'm using the slides from Professor Lazebny. So what is an edge now? Here you can perceive an edge nicely, and you can consider that these are also edges from dark background to bright. So when you really try to think about these edges, we identify sudden changes or discontinuities in an image. So intuitively, most semantic and shape information from the image can be encoded in edges. This is a more compact representation than pixels. The ideal situation is the artist's line drawing, but using these conventional techniques that we would study in this lecture, you would not be able to achieve this kind of a nice representation, which needs the object level knowledge and semantic knowledge that human beings have. But as you might know, the deep learning techniques have achieved near human like performance. Okay, so edges are caused by a variety of factors, sometimes the surface normal discontinuities, and then depth discontinuities. So here is this is the foreground and this area is background, and then surface color discontinuities. Right here the letters printed and non-printed gives rise to an edge, and then illumination discontinuities, the shadow area is dark and the outside is bright. So we already did the linear filtering, image blurring, and we understood the concept of separability. When you can have the filter, 2D filter as the outer product of two 1D filters, and the bivariate Gaussian is a good example of this. which we can represent as a product of two univariate Gaussians. And then we learned about median filtering also, which is not a linear filter but an order statistic filter, so not a linear filter. Okay, so now let's look at these edges, and here you can see a noisy image, a little bit noisy I think, and here you can see dark area, here is a bright area, here is a bright area, and there is some smooth transition over here from bright to dark. So if we plot, think about this horizontal line and take the row of pixels corresponding to this horizontal line and plot it, we would get something like this. And it is an intensity function of this horizontal line, and it goes from bright, maybe this is 255, to dark to bright, with this smooth transition corresponding to these places. All right. So if we can compute the first derivative of this function, so this is a transition from positive values to negative values, or positive values to lower positive values, maybe 0. So you get a derivative like this, and here you get a positive derivative like this corresponding to the transition. So from this, what you can understand is when you run the derivative operation, you actually detect the discontinuities, obviously. So the edges correspond to extrema of discontinuities. All right. So to do a derivative with convolution, we take this image as fxy, two-dimensional function, and then we want to compute the partial derivative with respect to x, which is actually we increment x by a small amount epsilon, subtract fxy at that location, and divide by epsilon and set the limit to 0, the definition of the partial derivative. But since these are discrete time signals, images, so we had to set epsilon equals 1 here, and approximately we can compute the first derivative. So since our convention of axis is this, x is in vertically downwards, y is horizontally rightwards, so this operation corresponds to a kernel of this nature. So this is actually the point of concern, and then we do the forward difference computation to get the derivative. So the associated filters we can see. Now before that we will do a brief analysis of this. So this is x-axis, this is y-axis once again. So think about to which image does partial derivative of the image with respect to x correspond to, and to which image does partial derivative of f with respect to y correspond to. So if you think about this, you will see horizontal transitions have been emphasized here. That means horizontal discontinuities have been discovered here. Here the vertical discontinuities have been emphasized. So therefore this corresponds to partial derivative with respect to s, this corresponds to partial derivative with respect to y. And then to run this, we can run kernels like this. Okay, so these are kernels, but there is no symmetry here, because this is the point of concern at which we compute the gradient. So if you want to make it symmetric, you would want to have 0 there, 1 here, and -1 here, which gives rise to the central difference formula. So here also, in regard to the vertical kernel, you can have 1, 0, and -1 corresponding to this. Okay, so to achieve a little bit of smoothing, we can define Prewitt and Sobel kernels. And this is the Prewitt kernel in x direction. So you can see the central difference formula that we saw before is there, but we take the contribution from the row left, the column left, and the column right also. So similarly, the horizontal kernel or partial derivative with respect to y And you can understand that in Sobel you have more emphasis to the column of concern, and here more emphasis to the row of concern. Okay, so now let's go to our coding window and see how the noise affects this gradient computation, and take that horizontal line of the image and compute the gradient, and then later on we can see how Gaussian smoothing can eliminate that noise. Okay, so now you can see in this piece of code I have loaded OpenCV, imported NumPy and matplotlib to be able to display images. Then rather than opening this stripe like image, which I can do actually, I'm creating an image of all ones of height 300 and width 400 of type uint8, and multiplying that by 250 and setting the column, several columns of pixels to 0 from 150 to 150 for all the rows, and then generate noise to add noise to this image. So mean is 0, sigma is 0.05. I want to normalize this image and then add noise. Then you generate noise by np random normal, and mean and sigma must be given, and the shape of that noise matrix would be im dot shape, same shape as the image, and then convert the image to a float image, and then do the im add using the CV add operation, image and the noise together, and then multiply that by 255, and then since some values can go beyond 255 and below 0, because of this noise addition, I am normalizing the image from 0 to 255, and then designating it as a uint8 array. And then I take this row, 150th row, to show the same effect as we saw in the slides, and then define a kernel -101, the central difference formula, and then run that with filter 2D. I don't know whether it is the appropriate thing to do, but it does the effect. And if I display this f and fx, you would see f is this noisy image corresponding to the bright background and the black stripe that we have, and this two spikes corresponding to the derivative with respect to, it's a single variable now with respect to x. So this is that noisy image, and you can see when you take this horizontal line in this fashion, you would see bright dark to bright transition, but of course with noise. Okay, okay, now if we think about this image gradient, actually it is a two-dimensional quantity, because we have partial derivative of the image with respect to x and partial derivative of the image with respect to y. We show it as the grad of f, is the grad operator. Then now if we consider this kind of an image, you can see in this direction there is a transition, but if you take the vertically downward direction, there is no transition. So we can think about which partial derivative is non-zero for this kind of a point, this kind of a patch. So you will notice that since our convention is this is x and this direction is y, the non-zero derivative is for partial derivative of f with respect to x. So if you consider this kind of image patch, non-zero one would be partial derivative of y with respect of f with respect to y. So we can consider patch of this nature, then both these quantities are non-zero. So gradient points in the direction of the most rapid increase in intensity, which is an obvious thing, I guess. And how does this direction relate to the direction of the edge? So it is actually perpendicular to the direction of the edge. So the gradient direction is given by theta equals tan inverse partial derivative of f with respect to y divided by partial derivative of f with respect to x. The magnitude can also be defined in this fashion: square the partial derivatives and get the square root. Okay, you can do nice things with these images. Solve for pixel values in target region to match the gradients of the source region while keeping the background pixels the same. Then you can have a beautiful, seamless kind of cloning. Have these nice effects. Okay, now let's look at this noise in this image and how noise affects the gradient computation. Now let's take this noisy one-dimensional image as we did in the code. So you can see there is the transition, and but the image is noisy. So you know that inherently when we run the gradient operator is an operator that amplifies noise. So therefore, if you run partial d by dx for this is a single dimensional function, you will see a lot of noise. So you cannot even find where the edge is, but in our example that we did, we can find the edge. So now what we do is we take the image and we run a Gaussian kernel with some sigma value, so that smooths out these noises when you convolve with this one-dimensional Gaussian kernel. After that we can get derivative, then this extrema of the derivative corresponds to the sharp transition or the discontinuity. Okay, so when you want to do edge detection, you have to first smoothen the image and then do the computation of the derivative. But actually, as you know, these two operations, since they both are linear operations, you can interchange. You can find the derivative of the Gaussian kernel and then run that on the image. So to find edges, look for peaks in this quantity. Okay, so derivative theorem of convolution is what I just hinted at. So differentiation is convolution and convolution is associative. So therefore, when you have d by dx f convolve with g, you can say f convolve with d by dx of g. So this is the derivative of the Gaussian. So you take the Gaussian is of this shape, and this slope is positive here, slope is 0 here, slope is negative here. So when you get the derivative here, you get this positive 0 and negative nature of this first derivative of the Gaussian. Then when you run that, you get exactly the same effect that you wanted. So we are back in the coding window. So you can see we took out one horizontal line of this noisy image. Then we filtered that, then we found out that it is noisy, but not as noisy as what the slides showed. Then after that, we can generate a Gaussian kernel. So I generated the Gaussian kernel of 11 width and standard deviation sigma 5, and then filter that image with the Gaussian, and then after filtering with the Gaussian, I applied the derivative kernel to that. So you can see the Gaussian filtered version of the noise has been cancelled. Then when you apply the derivative operator to that, you get a better, less noisier derivative. So you have to experiment with this sigma value and the kernel width and so on to get perhaps exactly what you saw in the slides. So as homework, you can think about running the filter, running the kernel on the Gaussian, so that you would be able to get the derivative of the Gaussian and then run the derivative of the Gaussian directly on the image. So this is up to you to decide. So here you may have to pad So you get the shape that you saw in the slides. Now after that, using this, you can run that on the image so that you can get this effect. Okay, I leave that as homework. Okay, so you saw how to get something like this coded. I gave you information so that you can do it on your own. But this is only for 1D, but can you do it for 2D? For that also I will show you some piece of code. So there you can see two-dimensional kernels, Gaussian smooth. So these are derivatives of Gaussian filters in the actually x and y directions should change. So this is in y direction, this is in the x direction. Which one finds horizontal and which one finds vertical edges? So this since this will respond to edges like that, it will find vertical edges. Since this responds to edges like this, it will find horizontal edges. Are the filters separable? That's a question for you to answer, because what we know that this Gaussian itself is separable, because we can write the bivariate Gaussian as a product of two univariate Gaussians. Okay, so we can briefly look at the scale of the Gaussian derivative filter. That's very important. Now, if you have sigma as 1 pixel, then this is for the zebra image. This is what you would get. I think they are displaying the gradient magnitude of this. If you have 3 pixels, you will have like this. If you have 7 pixels, you will have it like this. So if you have sigma as 1, you respond to small scale changes, and then when sigma is 7, you can see large structures that correspond to sharp transitions get emphasized. Smooth derivative removes noise but blurs edges, also finds at different scales. So the concept of the scale we can relate to the sigma of the Gaussian. So we'll briefly summarize what we studied. So when you think about the smoothing filters, Gaussian removes high frequency components. It's actually low pass filter. So we can have a image like display of the Gaussian. You can see here it's high and here it's low. And if you take a horizontal cross section of this, you will see the Gaussian shape. And it's a low pass filter. Can the values of smoothing field be negative? So the values of smoothing field are not negative. What should the value sum to? The value of the smoothing field should sum to 1. Constant regions are not affected by the filter. And the derivative filters are different slightly. Derivative of Gaussian filters are these. And then can the values of the derivative field be negative? Yes, of course. What should the values sum to? The values must sum to 0. No response to the constant regions. So high absolute value at points of high contrast. Now we will look at how to generate these derivatives of Gaussian filters. In order to be able to do that, we have to have this mesh grid construct. So you can see I'm generating an array of from -5 to 5 with steps point to 5, and I have y also. I give x and y to this mesh grid, and this gives me all x coordinates for the, I think, because I'm stepping by 20.25, I think about 41 times, this is the 41 times 41 array, I think. And this is also like that. This contains all the x coordinates and this contains all the y coordinates, and therefore we can use np-exp exponent and then get the bivariate Gaussian. So this will look like the bivariate Gaussian. We did not normalize it. Actually we should normalize it and divide by the sum of that. Because this is just to display, I will not do that part. So then you have the kernel array. So I had to define the array as a two-dimensional array, but you can see it is only the central difference formula that I have. In the middle row, I have -1, 0, and 1, and then then I filter that Gaussian z with that kernel and get zx. partial derivative with respect to x, and then filter that with respect to this kernel, which has a column -1, 0, and 1. That's a central difference formula you can see in the vertical direction, and then run that, and then I get zy. Then I plot zx and zy, and I have the contour plots also at the bottom. So you can see the two derivatives of Gaussians are shown here. Okay, so what we studied today was starting from what the definition of the edges. We understood that when edge detecting, we have to smoothen using a Gaussian first, and then run the edge detecting kernel. So edge detecting kernels can be using the central difference formula, or using a Prewitt kernel or Sobel kernels. But the smoothing operation and the edge detection kernel or the derivative operator can be combined, because these linear operators are associative. So therefore, we can generate the derivatives of Gaussian kernels. Also, we saw that when you think about a smoothing kernel, the sum of the kernel must be 1. If you think about a derivative kernel, sum of the entries in the kernel must be 0. Thank you.